Hi everybody, welcome to the Depth Shot. This time we have the Momona Yamagami about to talk about the muscle interface. If you and Momona has been very considerate to send the link to her slides and the PDF file in the chat box, so you can find them over there. Now let's everyone please join us to welcome Momona for her talk.
Great, thank you so much for the introduction. So again, my name is Momona, and I'm a fourth-year PhD student at the University of Washington in electrical and computer engineering. I'm working with Professors Steele and Sam Burden. I'm excited to talk to you today about how control theory could be used to decode user intent for users with and without motor impairments, and so show how such performance measures could be useful in comparing novel interfaces like muscles against manual interfaces. There we go. Despite advancements in technology, device accessibility remains a challenge for users with diverse motor abilities. Brain injuries like stroke or cerebral palsy are prevalent and could cause weakness, spasticity, and muscle tightness, which all contribute to difficulties interacting with devices. I am interested in understanding how we can improve interfaces for users with and without upper extremity motor impairments. The need for more accessible interfaces, especially for users with motor impairments, has motivated research to challenge ability-based assumptions for touchscreens and mice, develop adaptive algorithms, and model movement during device use. However, most of the research focuses on discrete interactions with minimal research into continuous interactions. I am investigating how we can better model continuous interactions for users with and without motor impairments. So what does a discrete or continuous task mean in the context of device interaction? To understand this, we can look at how people complete different tasks like typing, which I am defining to be a discrete task. So let's say you want to type in the letter H in Hello World on a keyboard. To complete this task, you can implement your intent to type H. But what if you accidentally typed in B instead because your cat jumped on your keyboard? This will cause an error that you will then need to correct by pressing backspace prior to pressing the desired key H. In the case of typing, I am defining this to be a discrete task because the error correction of pressing backspace is occurring as a separate and sequential interaction from implementing the intent to type H. If we use this definition, interactions such as tapping or pressing a button could be considered discrete interactions. In continuous interactions, however, like controlling a prosthetic or playing a racing game, error correction and intent are simultaneously implemented. Therefore, continuous interactions require new modeling methods that can predict what the user's intended actions are. So let's go back to the diagram again to take a look at how error correction and intent are implemented simultaneously in continuous tasks. And let's take the example of a person going down a path in a powered wheelchair. So let's say the person wants to go straight down the pathway to the end of the pathway where you can see that red circle in the back. And they can implement their intent to go straight by manipulating a joystick interface. However, they may encounter disturbances such as needing to move to avoid hitting a dog and ends up veering left onto the grass. But since the person wanted to go straight and not to the left, this causes an error between where the person is and where the person wants to be. And that means that the person must correct for their error in order to move back towards the right onto the pathway. Unlike the typing case, however, the error correction and intent are often implemented simultaneously by the user moving the joystick that controls the wheelchair. And in fact, errors don't just arise from environmental disturbances like avoiding a dog. They can also come from the person themselves through motor disturbances like tremors. If we frame device interactions in this way, we can see that if we can develop a predictive model that can separately quantify the person's intent and error correction, we may be able to develop algorithms to smartly enhance the person's intended actions while minimizing disturbances, minimizing errors arising from motor disturbances. The only problem is that there are no methods to separate intent and error correction in the time domain. However, there are useful properties from control theory that we can leverage with frequency domain analysis that could make it possible for us to perform this separation. So what is frequency domain analysis? Briefly, all time domain signals, like what we would obtain from measuring the position of the wheelchair or measuring the position of the joystick that the user is manipulating, can be represented by an infinite number of sine waves that occur at different frequencies and amplitudes. And this can be represented in the frequency domain as the amplitude and phase shift of each sine wave at all different frequencies. So for example, the sine wave A that you see here in the time domain can be represented in the frequency domain as a single signal at 0.1 hertz with an amplitude of 1. Similarly, the sine waves B and C can be represented in the frequency domain as a single signal that occurs at specific frequencies that are higher than the frequency for A. Frequency domain analysis is useful because we can separate signals that are mixed in time but separable in frequency. And so now let's go back to our problem at hand. We would like to separate intent and error correction, which are both implemented by the user at the same time with the joystick that they are manipulating. This is a signal that is mixed in time, and so we cannot separate the two in the time domain. However, in the frequency domain, we can obtain equations that relate these signals to each other. And then we can use tools from control theory to obtain models of the user intent and error correction algebraically. These models can then be used to predict user input in response to desired trajectories and unpredictable disturbances. In this way, control theory can be used to separate user input into intent and error correction for continuous tasks. And these tools could be useful in designing smart algorithms that can predict the desired user intent and minimize effects of disturbances. It could also be used as a performance metric to find novel interfaces that may make it easier for people to follow a desired trajectory or path. Today, I will be exploring the latter to determine whether this method can be applied to quantifying performance in muscle versus manual interfaces. So what are some non-traditional ways that we can manipulate interface devices? There are many different methods that are being investigated and used, but today I will be focusing on electromyography or muscle interfaces. Electromyography or muscle interfaces use electrodes on the skin to non-invasively measure electrical activity that is generated by muscle activity. We think that muscle interfaces could be especially useful for users who may have muscle weakness and find it difficult to interact with devices manually. Muscle interfaces can pick up weak signals even when the person is not actually moving, and the placement of the muscle sensors can be personalized and is adaptable to the user's ability level. The goal is that muscle interfaces could enable bilateral instead of unilateral interaction to decrease fatigue and errors, as well as encourage the user to continue using their affected arm. Here's what a person looks like playing a one-dimensional trajectory tracking game with their muscles on the left or with a manual slider interface on the right. As a proof of concept, instead of directly testing muscle and manual interface performance on a device like a wheelchair, we simplified the experiment to a one-dimensional trajectory tracking game that you can see here. Participants were asked to follow a yellow trajectory on the screen with a purple cursor controlled by either their muscles or a manual slider interface. The goal of this experiment was to determine whether muscle interfaces could improve continuous device control for users with and without motor impairments. For this study, I recruited 11 participants without motor impairments to perform the trajectory tracking task with either the muscle or the manual interface. I tested two different tasks. One is a velocity-based task, like controlling a powered wheelchair, where the position of the slider that the user is manipulating corresponds to the velocity of the cursor on the screen, and an acceleration-based task, like driving a car, where the position of the slider the user is manipulating corresponds to the acceleration of the cursor on the screen. We hypothesized that participants will perform worse with the acceleration-based task than the velocity-based task because the acceleration-based task requires an additional level of abstraction. We also hypothesized that since our participants without motor impairments are more acquainted with manual interfaces, they will perform better with the manual interface, regardless of the task dynamics. So for this study, I had two performance metrics. One is a standard time-based performance metric where I computed the error between the prescribed reference trajectory and the actual position of the cursor on the screen. I also computed a frequency domain metric based on how well the user's intent was being implemented. Since we know exactly what the user is trying to do, which is to follow the given yellow reference trajectory, we can measure how much of the user input corresponds to their intent and compare that against what their intent should have been if they were perfectly tracking the reference. And this metric ignores the user's ability to perform error correction. Going into the results, this graph shows the results for the time domain performance metric. The y-axis shows the error between the desired and the actual trajectory, so the tracking error. Therefore, lower values indicate better performance. The lighter yellow boxes is the performance for the muscle interface. And you can see there was not a significant difference in performance between the velocity-based and the acceleration-based task. However, if you look at the manual interface performance, participants found the acceleration-based task significantly harder than the velocity-based task. And now, if we look at the frequency domain performance metric that quantifies how well the participants formed their intent to track the trajectory while ignoring error correction, we can see that for the manual interface in dark purple, as we expected, participants formed better intent with the velocity-based task than the acceleration-based task. What was surprising was that for the acceleration-based task, participants formed significantly better intent with the muscle interface than the manual interface. And this suggests that for specific task dynamics like acceleration-based tasks, muscle interfaces may actually improve performance for users without motor impairments. So we have demonstrated that EMG interfaces could provide advantages for users without motor impairments for acceleration-based tasks like driving or playing racing games. But does this trend extend to users with motor impairments after neurologic injury? Today, I'll be showing you pilot data from 3 participants who have upper extremity motor impairments after stroke. The first 2 participants had more involved level of impairment, while the third participant was less impaired. Here are some of the preliminary results comparing the participants without motor impairments against our 3 participants who had a stroke. For the time domain error that quantifies the error between the desired and actual reference trajectory, it appears that the users with motor impairments perform better with the muscle than the manual interface. The graph also shows that participants with motor impairments perform significantly worse than the users without motor impairments. For the frequency domain performance metric, we can see that users with motor impairments develop intent with similar performance to our users without motor impairments. And in particular, we can observe that the users with motor impairments also develop better intent models with the muscle than the manual interface. And I will continue to collect data to see whether the trends shown here holds for a larger population. In conclusion, control theory could be useful for understanding the user inputs that correspond to intended actions, separate from correcting errors arising from motor disturbances. In the future, we eventually hope to develop smart interfaces for users with and without motor impairments that can enhance their intent while minimizing noise from motor disturbances.